Welcome to another module in this course, Microwave Integrated Circuits. In the previous module, we had seen the basic properties of the S parameters. In this module, we will continue our discussion on the properties of S parameters, especially as applied to two-port networks. So, we saw that in the previous module, we had seen that for two special cases, two special properties of networks, one is the reciprocity and the other is the losslessness. We can derive some special conditions for that the S parameters of such networks should satisfy. So, let us continue the discussion for two-port network. So, for a two-port network, our S parameter matrix will be something like this. If the device is lossless, if the let's first start with the condition for reciprocity. And this matrix should be symmetric. Okay. If it is lossless as well, in addition to being reciprocal. Now, here I must say something, that all passive networks are reciprocal. So, if I say, if I am referring to a reciprocal and lossless network, then it is like a network which contains only passive reactive elements like inductances and capacitances. There are no resistances in that network. So, if it is lossless, then we know the condition that S Hermitian where U is the identity matrix. So, if I expand my S parameter matrix, then I should get this S21 is equal to S12 because of the reciprocity, as we have already discussed. Further doing the derivation even further, so this S Hermitian S times S we can following. So basically, if we expand this this matrix multiplication, then what we will get is and then this should be equal to the identity matrix So, from the first equation and this equation. So, we have 4 sets of equations. So, if I label this 1, 2, 3, 4, then from this equation and this equation we can straight away write now from these equating the two, because this is common for them. So, basically this gets eliminated, this term. So, from here we can straight away write modulus of S11 is equal to modulus of S22. So, in other words, the S11 and S22 will have to have the same magnitude, and S12 from this equation, S12 square is equal to 1 minus S11 square. So, this in turn implies that modulus of S12 is equal to square root of 1 minus S11 square. Now, suppose we define since the S parameters themselves are complex quantities, if we define the S parameters in terms of phasors, that is a magnitude and an argument, S22 is equal to S11, since S22 magnitude is same as S11 magnitude, but then they may have different phase, different argument terms. So, that is why I have chosen theta 1 for S11 and theta 2 for S22, and S12, if I choose it like this and let its phasor be theta 1. Now, note, if I know the magnitude of S11, then I know also the magnitude of S22, and I also know the magnitude of S12 from this relationship, So, with this with these equations, so let us see what we have to. So, if we know S11 magnitude, we know the S22 magnitude, S12 magnitude, but we still have to find out the values of theta 1, theta 2, theta 12. So, at this stage we have 4 unknowns, theta 1, theta 2, theta 12 and magnitude of S11. So, to completely characterize the two-port network, at this stage we still need 4 parameters. Let us see whether we can further reduce the number of parameters. Now, we have another 2 equations as we saw. So, one other set of equations, one another equation from this matrix. If we go back to this matrix, we still have this equation, that is S12 conjugate times S11 plus S22 conjugate times S12 is equal to 0. So, if we equate this, let me rub out these terms. This might create some confusion. This is just a label for those equations. Okay, from that equation, what we can find is, now writing the S parameters in terms of the phasors, now simplifying this will give us, because S22 is same as S11. So, what we will get, all these magnitude terms will be cancelled, and what we will end up at the end is equating, so finally simplifying this, we yield this equation. Now comparing the left hand side and right hand side, we can simply write or so this is the final expression. So what we have done here is we have eliminated the need for another variable. So we at the beginning needed, well in the previous slide I said we need four more variables to completely characterize the system. So we needed 4. Now with this relationship we have reduced the requirement to 3. So if we know S11 magnitude, theta 1 and theta 2, then we can completely characterize a lossless and reciprocal 2-port network. Now let us see how we can directly calculate the S parameters. Now one way that we saw in the previous lecture was there was a formula relating the Z parameters to the S parameters. We can use that. So for any network we can first find out the Z parameters or the Y parameters and then use that formula to find out the S parameters. Or if we want to know the S parameters and we want to find out the Y parameters, we can do the reverse. But suppose we want to find out the S parameters from first principles, then how do we go on? So let us take a very simple example. Suppose, let me use a new slide for this. Suppose I have a simple network like this. It's a simple series reactance with say Z1 and Z2 being the characteristic impedances at port 1 and port 2 respectively. Now we have to find out all the S parameters of this system. Now first thing that you have to see is that this is a lossless system. This is also a reciprocal system. So since this is a reciprocal system, we should have S12 is equal to S21. Okay, now to find out say S11, we have to, so S11 is defined like this. So if we have A1 as the incident wave and B1 as the reflected wave, similarly say A2 is the incident wave at port 2 and B2 is the reflected wave at port 2. So then this is with A2 equal to 0. Now the question is, how do we make A2 equal to 0? Let us see whether we can make A2 equal to 0 or not. Suppose, consider we add a load Z2 at port 2. Now, what will be the reflection coefficient for a wave hitting the load Z2? Gamma L will be equal to Z2 minus the characteristic impedance. Now, we know that the characteristic impedance at Z port 2, this is port 2, is also Z2, and the characteristic impedance at port 1 is Z1. So, gamma L will be Z2, which is the load minus the characteristic impedance, which is also equal to Z2 upon Z2 plus Z2, and this is equal to 0. Now, if I write A2 in terms of B2, the way they are related is A2 is equal to B2 times gamma L, because gamma L is the reflection coefficient at this point. So, this relationship will be valid, but then since gamma L is equal to 0, so this is also equal to 0. So, we have, by connecting a matched load Z2 at port 2, we have eliminated A2. So, then we can now, if we find out, so the first condition for S11, recall that we had to satisfy was B1, S11 is equal to B1 upon A1 with A2 equal to 0. So, we have done that. Now, what is B1? What is this B1 upon A1 for this circuit? That we can say it is simply equal to the gamma in, isn't it? Gamma in is defined as B1 upon A1 with no restriction. The difference between gamma in and S11 is that for gamma S11 we have to have A2 equal to 0, but for gamma in it is not necessary for A2 equal to 0. But then the way we have made this circuit by connecting this load, we have eliminated A2. So, now A2 will always be 0, and therefore, S11 for this circuit will be equal to the gamma in for this whole circuit. By whole circuit I mean this circuit plus the load Z2. So, now gamma in itself we know is equal to Z in minus the characteristic impedance at port 1 upon Z in plus Z1. So, then if we can find out what is Z1, then we can find out what is gamma in, and then hence we can find out what is S11. So, let us see what is Z in for this circuit. This is the value of Z in, because Z2 is in series combination with Jx. Therefore, gamma in will be equal to Z in minus Z1 upon Z in plus Z1, which is equal to Z2 minus Z1 plus Jx upon Z2 plus Jx plus Z1. From this we can also verify, that if you want, you can verify that since this is a lossless and this is a reciprocal network, if you and by the way this whole thing will be equal to S11. Now, if we proceed similarly, we can also find out an S22, and we can verify that mod S11 will be equal to S22, and this similarity is because of this the lossless and reciprocal nature of this circuit, and due to the relationship that we had due to the conditions for a two-port network that we had derived earlier, a few slides earlier. You can verify that this modulus of this will be same as the modulus of S22. In fact, just from symmetry we can write down directly what will be S22. If S11 is given by this expression, S22 will be something like this. Just the Z1 and Z2 will be interchanged, and from this we can easily verify that S11 magnitude will be same as S22 magnitude. If you want to find out the S21 parameter or S12 parameter, how do I do that? Let us see. Now, S21 is defined as B2 upon A1 with A2 equal to 0. So, again we need to have A2 equal to 0. Now, coming back to our circuit, we saw that in order to make A2 equal to 0, we simply connect a load Z2 like this. But then what do we do next? Suppose I1 and I2 are the currents flowing into port 1 and port 2 respectively. Then we know that I1 is equal to the negative of I2. Now, if we write the same equation in terms of normalized currents, then we know we can write it like this. Now, I1 magnitude we know is equal to the normalized I1 is simply A1 minus B1, that upon Z1 is equal to A2 minus and I2 normalized is equal given by this. Now, we know this A2 has been made equal to 0 by this connection. So, from here we can simply write this down as A1 minus B1 upon square root of Z1 is equal to plus B2 upon square root of Z2. So, from here if we divide both sides by A1, then what we get is 1 minus B1 upon A1 upon square root of Z1 is equal to B2 upon A1 upon square root of Z2. So, we know that this is equal to S11. So, then this implies that 1 minus S11 upon square root of Z1 is equal to S21, and this is equal to, as we know, is equal to S21. Now, from here we can derive an expression for S21 will be equal to Z2 upon Z1 square root, and then the final expression for S21 that we should get is equal to so this is the final expression for S21. Now, this is the this is the basic property of a two-port network. We discussed a very simple case here, and for more complicated circuits we will need a more extensive network analysis to find a relationship between I1 and I2. But the basic procedure is the same, that you first find a relationship between I1 and I2 or between V1 and V2, and then express these I's and V's in terms of the normalized voltages and the normalized currents, and then you expand the normalized currents and normalized voltages in terms of the normalized incident voltages and the normalized reflected voltages, and then from that you equate the normalized the incident and normalized incident and reflected voltages and currents to find out the required S parameter. Now, there are some other applications of since as I said, a two-port network is very extensively used. It is the most common form of microwave network. There are some unique properties or unique results or unique parameters associated with a two-port network that I would like to show you how to derive it and what is the necessity of that. So, one important parameter that is frequently associated with all two-port networks is what is known as the input reflection coefficient. For this two-port network, we can write down the SB relationship between the A's and B's like this. And then A2, this incident at port 2, the wave that is incident at port 2, as I described earlier, is actually the can also be considered to be reflected from the load. So, then I should be able to write this equation as and this as now solving this first equation, I beg your pardon, solving the second equation, we get B2 is equal to S21 upon 1 minus S22 gamma L times this whole times A1. And then if we substitute this value in this equation, we get an expression for B1 in terms of A1 as S11 plus S12 gamma L times S21 upon 1 minus S22 gamma L. Now, from here we can find out an expression for gamma in, because gamma in, the input reflection coefficient, is simply given by this gamma in is equal to B1 upon A1. So, then this whole thing should be my gamma in, or I can write it down properly as gamma in is equal to B1 upon A1 is equal to S11 plus S12 S21 gamma L on 1 minus S22 gamma L. Now, this is a important parameter for all two-port networks, because as we saw that for good input matching, this gamma n should be as low as possible, preferably 0. Now, usually we do not have any control over the S11. Suppose we are given an amplifier, the S11 is constant, but we do have some control over, say, the gamma L. And so, if you see, if gamma L is equal to 0, then gamma in reduces to S11. Now, similarly, in the same way that we have written an expression for gamma in, we can also write an expression for gamma out, which is called output reflection coefficient. And just following symmetry, you should get the value of this gamma out as so. Again, just like the same case as the gamma in, the value of gamma out also is preferred. In many applications, we prefer the gamma out to be as low as possible. And so that's how both this gamma in and gamma out, if they are low, then it's considered to be a good matching. Now, one simple example that I would like to show here is that of an attenuator. An attenuator has a S parameter matrix. A simple attenuator is a two-port device whose whose S parameter matrix is given by this matrix. Actually, this is S12 also, this is 0. So, both S11 and S22 are 0, and gamma out therefore should be equal to simply S21 gamma S12. Okay. Now, since S upon 1 minus S11 gamma S, where this gamma S is the generator reflection coefficient. So, just like the load reflection coefficient, we also have the generator reflection coefficient. Now, since S11 is 0, so this should be reduced to S21 gamma S S12, and then since it is a reciprocal device, so we have S21 square. If I directly write the magnitude like this. So, in order to reduce gamma out, we see that either we make gamma S equal to 0, or we design our system such that this S21 magnitude square is as low as possible. So, in summary for this lecture, I would like to state that in this lecture we have covered the basics of not the basics, we have gone little more in depth into the properties of the S parameters for two-port networks, whereas in the previous module we had only considered the properties of any port of any general network. Here we are specifically seeing the properties of two-port networks, since as I said, two-port networks are very widely used, and two of the major parameters that are associated with impedance matching are the gamma in and the gamma out. Now, as we saw, writing down the equations for even a two-port network is quite involved. There are lots of equations involved. So, now imagine if we have a number of two-port networks connected with each other, or a two-port network connected with higher number of with a device which has either say 3-port or 4-port. So, then keeping on writing such equations becomes very complicated, and it might take a lot of time, and it is difficult to analyze generally. So, in order to make life simpler when we have a large number of ports, there is a technique called signal flow graphs, and as we shall see in the next module, the signal flow graphs significantly reduce the complexity of the signal flow, especially when we have incident and reflected waves to consider. And there are some methods to analyze such signal flow graph diagrams, so that we can find out these say gamma in or gamma out, the input and output reflection coefficients, which we have derived here using equations. We can simply use a signal flow graph to find it much quickly. So, that is something we will discuss in the next module. Thank you.